Hello and welcome to another Jacobs Hall video tutorial. My name is Adam Hutz, a design specialist with the Jacobs Institute, and today we're going to be talking about flexible parts, specifically this flexible part. This is a gasket, and it was submitted through Jacobs project support by an innovation catalyst team. Prototyping flexible parts can be really tricky. Most 3D printers, just by the nature of fused deposition modeling and stereolithography printing, favor rigid parts. A printer lays down a bead of molten plastic, which then cools and solidifies, or resin is cured solid by a laser. There are a few 3D printers that can produce flexible parts though. In our advanced prototyping lab, our Objet 3D printers can produce very high fidelity soft parts, but they're less elastic than some parts demand and tend to tear under stress. The Form 30 3D printer can also make use of an elastic resin, but at a durometer shore hardness to 50A, roughly equivalent to a pencil eraser in flexibility, this material may still lack the properties you seek in a truly elastic part. At this point in the prototyping process, we begin to explore casting. Casting can have a little more overhead in terms of labor than 3D printing, but the range of material properties you can achieve is much greater. In this particular case, we're looking for a silicone part with a rough shore hardness of between 10 and 25A, closer to the consistency of a rubber band. Silicone also has the advantage of not sticking to anything except silicone while curing, meaning we can actually 3D print our mold in PLA. Here you see me bringing the part into Fusion as a step file, and then designing a mold around it. I'm going to speed through this process, saving the details for another video, but some broad considerations here are draft angles, or preventing too many undercuts, although it bears mentioning that silicone is capable of peeling out of molds that rigid parts would be fully stuck into. Alignment features, these spheres you see me placing help align the two mold halves, so you get a perfect part through alignment every time, and some cavities in the sides for prying apart the mold halves later. And of course, a gate and sprue where I'll either pour or inject the two-part silicone material, and then another hole through which air will escape. Once the PLA mold has been printed, it can be clamped or rubber banded together. The silicone I'm using is a smooth-on product that cures to a roughly 15A shore hardness in about 4 hours. Best practice is to mix your two parts together thoroughly, stirring and scraping the sides for between 30 seconds and a minute, depending on the pot life of the material, before pouring into a new cup for final mixing. The new cup makes sure that no unmixed materials from the sides contaminate the final pour. Once everything is mixed, we use a vacuum chamber to degas the silicone. A vacuum chamber removes most of the air that is mixed into the silicone as bubbles, and this is especially important when casting clear materials or when you have thin walls or small features. If your part is lower fidelity, or if you're making a mold for a part with larger features, you could sometimes get away without degassing your silicone, or with other DIY strategies for reducing the amount of bubbles introduced through stirring. At this point, the silicone can be drawn into our syringe and injected into the mold. If you don't have a large syringe, this particular one is from Tap Plastics, or you can get them online. You can use a funnel or build a larger well directly into your PLA mold. Material is injected at an angle so air escapes upward as the material fills the mold, and the part is left to sit for the 4 required hours. With thoughtful mold construction, demolding can be fast and easy. Silicone is forgiving during the demolding process since it doesn't chemically bond to PLA, and a 15 shore A part can be stretched and pulled out of any undercuts or steep draft angles left in the mold. After the part is demolded, the mold can be used again right away to cast more parts. Casting can feel intimidating because it can seem messy, sometimes requires a scale for precise measurements, and cure inhibition when using platinum silicone can risk ruining both a part and its mold. But most room temperature casting is as easy as mixing and stirring a few compounds, pouring the results into your mold, and waiting patiently for your part to be done. The final step here is to cut away the sprues and to trim off any flashing that occurred around the parting line between your mold halves. Flashing is common in casting and is one of the main considerations when developing the initial mold. Taking time when developing your mold to make sure you have good alignment can make this final post-processing step incredibly fast and ensure you're producing high-quality parts every time you cast. That's all for this quick tutorial. If you have an idea for a tutorial you'd like to see, or want to talk more about this process, feel free to contact me at adamhutz@berkeley.edu, or the Jacobs Hall staff at jacobsprojectsupport@berkeley.edu.